Good evening, everyone, and welcome to this October talk in this year's speaker series, Dawn of the New Space Age. My name is Associate Professor Mike Ireland. I'm going to be the chair for tonight's talk and questions. Before we begin, however, I'd like to acknowledge and pay respect to the traditional owners of the land on which we meet, the Ngunnawal people of the Wiradjuri Nation. It is upon their ancestral lands that the Academy of Science is built. As we share our knowledge, teaching, learning and research practices, may we also pay respect to the knowledge embedded forever within the Aboriginal custodianship of country. I'd also like to thank our series sponsors for this evening's talk. Hopefully you've enjoyed Jura Wines at Geostation and Edge Catering. So tonight's talk will also be available afterwards on the Academy YouTube channel, in case you missed bits of it. For those of you in the audience that have phones, please put them on silent. But if you're on Twitter, we would love it if you could contribute to online conversations by using the hashtag #SpaceDawn, which I think is not up there, and @science_academy. So with that, I'd like to introduce tonight's speaker, Dr. Helen Maynard-Casely. Dr. Maynard-Casely is an instrument scientist for ANSTO. So she works with the Wombat instrument there. Her expertise is on the study of molecules and ices under pressure, sometimes extremely great pressures, and that's what she'll talk about tonight. She studied planetary science at the University College London, UCL, before completing a PhD in high-pressure physics at the University of Edinburgh. She's passionate about understanding the planetary bodies in our solar system and about promoting science to a wide audience. She's often a contributor for both Cosmos magazine and features a column in The Conversation. Hopefully you've all read The Conversation, and hers is called The Shores of Titan. Tonight, Dr. Maynard-Casely will take us on a journey to explore our solar system and the formation of the planets within. Please join me in welcoming Dr. Maynard-Casely to the stage.
Wow. Thank you all very much for being here. It's an absolute pleasure to be here and talking to you guys. When I talk to people, I like telling you as much about what we don't know about things as much as what we do know. And that comes from when I was a teenager, finding people telling me, oh, we know this, we know this, we know this. And I was like, oh, by the time I get to be a scientist, there'll be nothing left to know. And of course, as I've become a professional scientist, I found that's very much not the case. And as most scientists, the older I get, the more I realise more we don't know. One of the big frontiers, especially for planetary scientists, is what's in the interior of planets. And that's what I'm going to talk to you about today. And actually, I'm going to talk about the planets in general in terms of what we understand in our solar system. But of course, that's changing. On a almost monthly basis, we are finding new and exotic exoplanets. And as of course, only today, I discovered a whole new part of astronomy with this new killer nova, collision of neutron stars. But we don't actually have to go too exotic other than under our own feet to find out something that we really don't know. The interior of the Earth is still poses a lot of questions. And so, okay, it's under our feet. Maybe all we actually need to do is to go and dig a big hole. Now, that seems sensible, right? Let's just start digging a hole. What do you think is the biggest hole that's ever been dug in the Earth's surfaces? Oh, someone's said the answer already. Fantastic. But how deep is it? So it is in Russia. How deep? Do we think it's about 1 kilometre deep? No. Higher? Oh, higher. We can play higher, lower. Higher than that? What do you think, sir? Ooh, that's good. And that's something like the Rift Valley, where the plates are actually pulling apart. It is deep, but it's not 25 kilometers deep because, as you suggested, the deepest hole is in Russia, and it is 12.6 kilometers deep. So That's a really good effort. That's into the sort of what we call the continental crust, the crust that we all live on. And this is the deepest research hole, I should say. I think there is an oil company that claimed they have gone a little bit deeper than that, but only by a centimetre. And as a result of this, the Russian scientists that excavated this hole, we know a lot about how the continental crust changes, how its minerals changes, how porosity changes, how all sorts of things change. So that's a pretty good effort, right? However, there's a lot more still to go. The center of our Earth is actually 6,400 kilometers below our feet. And there's a lot of changes that happen in that's sort of signified a little bit by the color. We go from a dense, right in the center, a very dense, solid core, to as you move out from the center, we actually have a liquid mantle, which plays a very important role in our lives on the surface of the Earth. And then we have this big plastic mantle. Now, people often think of lava and that whole mantle area, so I'm talking about this whole area here, as liquid, but it's not liquid. It's actually, it's so hot that the rocks are all plastic and can deform. So they're not liquid, they're plastics. But it's how do we actually understand all those conditions? How do we even know where we've only dug a hole that's 12 kilometers thick? I should confess in this that a lot of what we know on the Earth has come from seismology, from monitoring how earthquakes have propagated, have moved through the Earth's interior. I'm not going to talk about seismology purely because I wanted to talk about the planets generally, and we've only really got one seismometer on another planet that works, and that's the Moon. And they're all on one side because we only landed on one side of the Moon. And they've been very useful. We know a lot about a bit of the Moon, but we've not got a global network like we have. This is so important, I should say, that NASA are currently planning to dig a hole and put a seismometer onto Mars. It's going to be called the InSight mission, and hopefully we'll be launching, I think, early next year. So that's something to look out for. So that will go there and basically sit out and look out for Mars quakes. There wouldn't be earthquakes, I suppose, and try and find more about the interior of Mars. But how do we more generally, ignoring seismology, know anything about the inside of planets? Well, we've got a number of observations that we can use. For most of the planets in the solar system, we know their mass, we know a bit about their surface chemistry, mainly from sending spacecraft to look at them, and we also know about their magnetic fields, and something about the magnetic fields can tell us a lot about how planets differ, especially. And then we can also follow up those observations with experiments. We can do them both in the laboratory, where we actually mix things and recreate the extreme conditions, but we can also do them in the computer. We can do theoretical experiments that recreate some of the conditions, but also give us an idea of some weird stuff that's going on, and I'll talk about that later. So luckily for us, in our solar system, our planets come in 3 convenient little sizes. I actually make no apology for calling Pluto a planet. I believe that it very much is a planet. In fact, I'd like to widen the definition, and I think that anything that's basically got itself together enough to be spherical should be called a planet. But that's just me as a geophysicist wanting to say that. So in that case, I think of the icy moons. So Jupiter and Saturn and Uranus and Neptune have a suite of large icy moons that are, from my point of view, as interesting as planets. They have a change in their interiors. They have different materials, different extreme conditions. And I think they should be, they very much are studied as planets. If you think of Ganymede, which is the biggest moon in our solar system, it's actually bigger than the planet Mercury. So it's definitely worth talking, and I will talk a bit about it today. The medium planets are the ones that we know the best. We're living on one, the terrestrial planets. Mercury, Venus, Earth, and Mars. They're mainly rock and iron. And how does that rock and iron make the variations that we see? And then we have the large planets. And in our solar system, that's our gas giants. I'm going to talk today about Uranus, because I don't think any people talk about Uranus enough, and I think that's just because it's got a silly name and people are scared of talking about it. So I think Uranus gets a bit of a bad deal, and it's certainly in my favourite gas giant, and I'm going to talk about it. So going over those observations that we have, the best way that we've had to sort of observe the masses is to send a spacecraft of known mass round those planets, and that's how we've really accurately got the masses of the planets. So, for instance, we can see a change that immediately, and the average density immediately gives us an idea of what those materials are made of. So, for instance, the planet Saturn has an average density of less than 1 grams per centimetre cubed. So that means if you could find a bath big enough, Saturn would float. But that immediately signifies to us that the planet's not made out of rock, it's made out of gas, whereas Earth has an average density of 5.4 grams per centimetre cubed. And so that's more like rock. So that's immediately from our mass and the average density, we can get an idea of what's in the planet as a total. We can then look at the surface of the planets, and this is where some of the amazing missions that both NASA and ESA have sent to our planets have given us a wealth of information. They can look at light reflected off the surfaces and find something about the surface chemistry. Now that's really interesting from a geological and mineral perspective, but also gives us a grounding point. So we know from the mass and the average density what the planet as a whole is made out of. From the surface chemistry, we can guess what the lightest material is. So on our medium-sized planets, on our terrestrial planets, that lightest material is rock. And so we know that anything heavier in the middle has to be something heavier, so something like metal. If you go to a planet or a moon like Ganymede, it's actually ice is the lightest thing on the surface. And so you know that the interior is probably going to be more rocky. Maybe it goes up to a little bit of metal up there. And if you ever want to lose an entire afternoon, I recommend the HiRISE instrument, which is on the Mars Reconnaissance Orbiter. HiRISE has an amazing website where you can look through their gorgeous pictures. There's a few that I've highlighted here. They have a whole series that I really like that are just tracking the Curiosity rover. And so you can see the little tracks moving as well. So that's a way to lose a whole afternoon. But then, of course, how do they annoy their neighbours? How does those magnetic fields? And the magnetic fields of these planets change quite greatly. So we often think that Mars and Earth are very similar, especially in their interiors. They have a rocky outside, probably a rocky mantle where things move around, an iron core. But Mars doesn't have hardly any of the magnetic field. It's very, very weak and very transient, it would seem. Whereas Earth has quite a big and active magnetic field. We see it if you've ever been lucky enough to see the Aurora Australis, the southern lights. And it protects us from some of the more energetic particles coming from the sun. And so it's very important to us. But how is it so different when those planets are essentially the same? So I'll talk a bit about that. But I'll give you an idea about extreme conditions. And essentially, my career to date has been about recreating extreme conditions in the lab. So I'll talk a bit about how we do that and the sort of conditions we're aiming for. So here I've said the centre of the Earth is 6,000 degrees C, but we don't actually know that for sure. That's a guess. There are a lot of very clever scientists working on that, but at some point, probably when somebody younger in the room is going to work that one out. For scale, it's always good to think about how hot really 6,000 degrees C is, and I like thinking about my oven. I've recently got into sourdough baking, and I've had to put my oven up to 230 degrees C, and I was scared enough at that. So 6,000 degrees C seems a lot. But then, of course, you've got the weight of the overlying rock, and that actually puts an enormous amount of pressure onto the materials in the centre of the Earth. In fact, we know this a lot better than we know the temperature. We know the pressure at the centre of the Earth is 3.6 million atmospheres of pressure. Now, pressure is a harder variable, a harder thing to sort of to communicate to people. In the UK, we often use the sort of length of a double-decker bus as a standard length unit. Here, I've noticed the area is measured in footy fields. I would like for pressure to be, its unit to be elephants in high heels. And this is based on that if you take one fully grown African elephant and you put him in some stiletto heels and you persuade him to balance on just one of those heels, he will generate 10,000 atmospheres of pressure underneath that heel. And that line is, as you can see, right up the top there. So in terms of 3.6 million atmospheres, it's very small. Now that is still quite a big pressure. That pressure is enough that if you had liquid water just at room temperature and you pressurized it, it would freeze because the molecules don't want to be liquid anymore. Generally, molecules, when you push them together, they're like teenagers. They don't like being together. They'll find new and imaginative ways to rearrange to be the furthest away that they possibly can from each other. So that's the sort of conditions that we're looking at. But how do we make those conditions in the laboratory? And I admit elephants are not the best thing to work with. And for this, we use diamonds. So diamonds are very much not only a girl's best friend, but a high-pressure scientist's best friend. And as we have another diamond envelope cell scientist in the audience, Jodie down there, who told me a story of her using diamonds and them being consumables. You take two normal gem quality diamonds, you sometimes like them to be a little bit better quality, you turn them sort of one upside down, and then you flatten the pointy bit, and you make a culet. And in that culet, you sandwich a piece of metal which you've drilled a hole in. So you drill that hole in, and then you can put your sample in there. Now, diamonds are really useful, not just because they're really hard, so you can make them very, very small, but also put a very moderate force on them to generate very high pressures. But also, they're clear, so you can see what's happening at the same time, which is great. So here, you can looking down a diamond anvil cell, and you can see the sample sat right in the middle, right there. So that's the sort of sample size you're looking at. And just for scale, so there's the piece of metal with the hole drilled in, so the sample sort of lives there. That is my little finger. So this is not something you do before you've had your morning coffee. You've got to make sure you're nice, steady hands before you load. Now, the great thing about diamond anvil cells is that you can put these samples under very extreme pressures. The cells themselves are quite small. They actually fit in the palm of your hand. And they're very transportable. So you can take them to lots of different facilities, like, for instance, our synchrotron down in Melbourne. And synchrotron X-rays are particularly good here because you can make them very, very thin and very, very high energy. And you can throw them through the samples, and you get a pattern coming off. And that pattern you can use to work out where all the atoms are sitting in your sample. So you can see how the atom's changing. So like I said, with water, when you freeze it, you can tell whether it's gone from a liquid to a solid, and you can see other changes, which I'll talk about as well. If you put something absorbing in there, well, if your sample doesn't absorb itself, you can also put lasers down there. And then the absorber will absorb all the energy from the laser and heat up the sample. So this is how we can recreate the conditions in the center of the Earth, right here in the laboratory. So it's really, really useful. So with those sorts of techniques, what have we found, at least for our own Earth? And I said about how those crystal structures, how materials change as you pressurize and heat them. Well, we see that as you go down through the Earth. There's sort of 4 representative materials from different parts of the Earth. So if we go to our crust, we have a normal pyroxene mineral. Most rocks that you'd fill out, anything that's sort of vaguely volcanic, will have a pyroxene in it. And that's it's very indicative by it's got a nice silicon atom with some oxygen sat around the outside. Now, if you start compressing that and you get to the mantle, this material, a spinel, becomes much more common. And you can see how much closer packed it is. They're trying to rearrange themselves so they're nice and neatly ordered space, but they're having to make more room. And so everything packs in. If you get further into the upper part of the mantle, before big things become liquid, you get this perovskite material. And at that point, the silicon atoms are so compressed, they're like, oh gosh, I've only got 4 oxygen, I've got room for 2 more, and grabs another 2 oxygens as well. And so you get these changes in materials as you move down. And a lot of these changes are responsible for the layers, the onion-like layers that we see in the Earth. And you get all the way to the very core of the Earth, and you have this very dense packed iron. But I should say that one of the big mysteries we have at the moment is that we know it's iron, and we know there's a lot of nickel there, and a lot of that has come from study of meteorites, where you can see meteorites, which are planets that tried to form and didn't quite get there and broke apart and then eventually fell onto the Earth. A lot of those are iron-nickel mixtures. But there's a missing element. Our core is is light enough that we know that there's a light element in the core. And it changes year from year as to what that is. I think current favorite is that it's hydrogen, but it might change again. So that's a big mystery that we need more experimenters, hopefully some younger people in the room, to go forward and to find out what is that light element in our very core. So I've talked a bit about a medium-sized planet, so let's talk about a small planet. I'm going to talk about Ganymede because it's one of my favourite icy moons. I've got a few favourite icy moons. But Ganymede stands apart from them all because it has a magnetic field. It's slightly unusual. So as soon as we have a magnetic field, that suggests that something energetic is going on in the centre of this planet. Like in Earth, we think that our magnetic field is being driven by the core and the liquid, the solid inner core and the liquid outer core. We're not quite sure that anything like that can happen on Ganymede, so it's a massive mystery as to where the magnetic field is coming from. But this really nice theory also came through that for a long time, so a lot of you might have heard of Europa, which is Ganymede's sister and probably more famous sister. And one of the reasons Europa is so famous is because it was discovered by the NASA Galileo spacecraft to have a planet-wide ocean underneath the ice crust. Now, people tended to ignore Ganymede because the thought was that, yes, it would probably have an ocean, but it was so big that that water would freeze, like I said with the elephant, under the pressure, and that would cause a layer of frozen ice between the rock. And the idea is that you need the liquid in contact with the rock in the center, at the bottom of an ocean, in order to have any hope of there being life. And so for that reason, for many years, Ganymede was sort of shunned as a potential place for molecules or maybe even little fishes to have developed. But this theory came out only a year or so ago, and they've come up with this idea that instead of one ocean, Europa could have 4. And it could go from one solid ice to liquefy to a different ocean, and then you get this weird layer where you have ice 3, and I'll explain what ice 3 is, snow that falls downwards because it's denser than the surroundings. And then you get another liquefied layer, and then another solid, and then a liquid layer before the very rock at the stone. So they called this a club sandwich model, so these very different layers as you go through. But why is that? And in order to understand that, we need to know a little bit about water and how it changes under pressure. So you're all probably very familiar with the classical phases of water. You have your vapor, your gas, your liquid, and your solid. That's great. And you have, and you can see the sort of pressure ranges and temperature ranges along the axes there. Now, we're going to just look at the interior of Ganymede, which is that bit in there. But there's actually some changes you can see even from this. So we'll zoom right into that, and we can see the changes there. So instead of just one big solid area and the liquid area there, you can see that there's different areas there. And what these are is the different forms of ice. So water molecules can arrange themselves in lots of different ways in response to the conditions that they're under. In fact, water is actually really, really diverse. It can actually form 21 different forms. It's just bog standard water that you would find in your freezer. In fact, this structure here, ice 1, is the bog standard water ice that you find in your freezer. If you were to take that and to compress it from your freezer temperature, which is around there, at -20, you would actually find that it would, and at around 200 megapascals, it would actually liquefy before freezing to this ice 3, which is a very different structure. Now, each of these materials, and we'll call them different materials, have different physical properties, different strengths, different ways of propagating heat, different ways of moving energy around. This one I like in particular is ice 6, which is the one that they think is, a lot of it is in Ganymede. And it has a very different crystal structure. So ice 1 we know is hexagonal. That's why we get beautiful snowflakes. Ice 6, you get square snowflakes because the structure is so different. That's really, really cool. Now, what we're going to do now, and I talked about digging a hole into the Earth, but we're going to dig a sort of virtual hole into Ganymede. And before these people released this new theory, this is what we thought would happen in the center of Ganymede. And this is, again, why Ganymede was shunned. We go from the surface of Ganymede is actually around minus 120 degrees C. So give me a bit of liberty, I've chopped off that excess. And we keep digging and digging, and then all of a sudden the pressure starts going up. And this is where you liquefy and you get your ocean. So this is why we think Europa has an ocean, Titan has an ocean, even Pluto we think has an internal ocean. In fact, now that we thought it was very unique when we discovered with Europa, and now we realize it's probably old hat, and that most of these icy moons have oceans underneath their solid surfaces. So it's very exciting. And this is the thought that, you know, in Ganymede, most other icy moons, the rock starts at some point along here. But with Ganymede, it keeps going up to here, and you would freeze and get solid ice. Now, what these researchers did was, instead of considering the interior of Ganymede to be pure water ice, which we know it isn't. We know there's a lot of other stuff. We know there's a lot of salt there. Salt, there's two different potential sources and two different forms that salt could be. But what is the effect that salt has? It has an effect of freezing point depression. So if you've ever tried to cool your beers down on a really, really hot day, the best way to do it, and this is a recipe that I'm happy to share with all of you, is to take 1 cup of salt to 3 cups of water, and then throw in all your ice. You can get an ice bath down to -20. And that's because the salt's there dissolved in the water and basically stopping the water molecules from freezing, and so they can get a lot colder. So this is the freezing point depression. And this has a similar effect on the solid forms of ice under pressure. You can actually get to a point where the salt stops the water from freezing. And actually, you get some very weird effects where at some point it squidges the salt out and it goes, I'm going to freeze anyway. And then it liquefies again, and then it freezes again. So this is the very weird thing. So basically, instead of, if you dug this hole, instead of moving the phase boundaries, I've moved the wiggly line, but you can get solid, liquid, solid, liquid, solid, liquid, which is why you get that potentially very interesting club sandwich. And it brings up some really nice ideas. If you do have those 4 separate oceans within Ganymede, could you potentially get different bugs living in each different one, different bacteria occurring? That's something definitely to look to in the future. So we've talked about a medium-sized planet and we've talked about a small planet. But we're going to talk about the large planet, and I'm going to talk about Uranus because, as I say, nobody talks about it, which is a shame because Uranus is really weird compared to many of the other planets. Well, for one, it looks like it's had a very good night out, and its rotation axis is pretty much on 90 degrees, so it actually rotates like this. And at the moment, I think it's the southern hemisphere has just had a 20-year summer, and it's got a very, very long winter coming. Because of this very, very weird rotation. So not only is that happening, but if we think about the interiors, the conditions there are very different to the Earth. They're much more extreme. So on Earth, we think the temperature is around 6,000 degrees C. The center of Uranus, more like 8,500 degrees C. And with pressure, it's even more extreme. It's beyond the 3.6 million atmospheres that we can just about recreate with diamond anvil cells in the laboratory. 13 million atmospheres, I have to say, I put my hands up, we can't do experimentally just yet. We're working on it. So this is where the domain of theoretical colleagues come in, and they can start to look at those materials that we think are in the center of Uranus and try and do something, simulate those conditions and see if our understanding of the water molecule and how it's made up is enough to predict the behavior. So I realized I've given the game away and talk about water molecules. So we think the center of Uranus is made out of mainly ammonia, water, and methane. And I'm just going to pick the one for continuity. We're going to talk about water again. Because water, it would seem, under high pressure and high temperature, theoretically, does some very strange things. So if you keep pressurizing water with temperature, you get to ice X, it's ice 10. And this is symmetric ice. It's ice where it has pretty much 4 hydrogens associated with it. Now, what we think happens if you take that really, really super dense ice structure and you warm it up, at some point, the hydrogen decide to go, right, you know what, I'm fed up with the oxygen, I'm just going to flow. And that's what we think happens, that the hydrogens start flowing around and the oxygen are left behind. So the reds are the oxygen and the whites are the hydrogen. And they flow around, but they're not just atoms there, they're charged, they're protons. And what happens when you flow a charge? You generate potentially a magnetic field. And that's where we think the magnetic field of Uranus and Neptune is coming from. It's coming from the very, very extreme and strange properties of water ice under pressure. Now, again, I personally, as an experimentalist, have tried to make this. And what happens is that you put your metal gasket in there, and this water starts eating the metal gasket because the protons are very acidic. This stuff is really nasty. So we've done very barely scratch the surface in the experiments we can do in these weird materials. So this is water that can eat metal. It's very, very strange, and it's something that we do need to know more about. So with that, I'll start to sort of wrap up a little bit. But as I mentioned earlier on, I like being a planetary scientist because I tend to think of it as a growing business. And thanks to my astronomy colleagues, it very much is. We're only day upon day, it would seem, finding brand new exoplanets which are bigger and different and just strange conditions. And so it's only widening the amount of materials that people like me can go off and study and apply to planetary science. So it's certainly a really exciting place to be, and I hope that many of you would like to do it in the future as well. And so with that, I will acknowledge my co-conspirator in this talk, Carl, whose artistic license made this so beautiful. And thank you all so much for listening.
This one work too? Maybe if I switch it on, it works. Well, thanks very much, Helen. We have plenty of time for questions now. And I have lots of questions, but we should actually start with the audience. So anyone can ask a question. We have 2 roving microphones. One at the back.
Good evening. My question relates to ICE and the movement of those protons as it's through. In order to generate the magnetic field, would those protons need to effectively form whirlpool-type currents because of the planet's rotation? Because my recollection from a long time ago is that it's those Coriolis effects that generate the magnetic field on Earth.
Yeah, so your magnetohydrodynamics is probably better than mine. But yeah, on Earth we think that, there's like 3 sort of whirlpools or vortexes that are made within the core and the liquid, the solid inner core and the liquid outer core. We think it's the differential rotation between these that whip up the liquid inner core to generate these vortices. Yes, there's a big debate over, especially the interior of Uranus, is whether it's conductive, whether it's able to have convection, or whether it's stagnant, and it doesn't. And a lot of the evidence for it being stagnant is the fact that the top layers of Uranus, the surface of Uranus, is the coldest place in the solar system. Goes down to 20 Kelvin. So if there was active convection, active things moving through, you would expect to see some heat at the top there, like you do with Jupiter and like you do with Saturn and to some extent Neptune. So Uranus is a big puzzle in that respect. So it could be that there's a stagnant layer sitting over a convective movement regime, because it's hard to imagine how you can have such a big energetic system without things starting to convect. But yes, certainly what is anticipated and I've seen has been worked out is that you get these sort of cells developing, and those were what generate the magnetic field, for sure. But thank you. Oh, yes.
Down here. So that question was, what's the biggest exoplanet that scientists know of?
Unfortunately, I should say, this is where I have to say I'm not so sure. You'll probably have to go find another scientist, because I'm not an exoplanet person. I tend to just stop when we get to the end of our solar system at Pluto. I'm like, oh, okay. So in our solar system, of course, the biggest planet, which you know, is Jupiter. But my understanding is that we found exoplanets that are much, much bigger than Jupiter, many sizes Jupiter. Because then you get to the point where it becomes a star in its own right. So there's probably a limit, an upper limit to when something can be a planet. But yes, for sure, we found much bigger planets. And those are really interesting because they're much more extreme conditions than we even can think about just yet. So one day, maybe you'll be the expert of that.
Okay, so while waiting for the next question, I'll have a follow-up question on this question here. So I was in a meeting in Nice, France, a couple of weeks ago, talking about measuring the diameters of stars in order to determine the density of exoplanets, because one of the biggest errors is on the diameters of the stars, and you get this ratio. But no one really knew how accurate do we need to know the density of exoplanets before geophysicists stopped being interested anymore. So the context is we know the abundance of magnesium and iron in the stars, and you can sort of think about what the planets will be made of. But what sort of accuracy are we going to need on the density of planets?
You're going to need to know to 1 grams per centimetre cubed, pretty much. So we want to know whether it's rocky, gassy, or icy. At the moment, that's, I imagine, how we would define it. And there are people who are beginning to develop models or variate what we know about the terrestrial planets and apply it to like super Earths, because we're discovering terrestrial planets, rocky planets that we think are much bigger than Earth. But of course, how does that even work? How does it not even implode on itself? Or how do you even live on the surface of a super Earth where the gravity is going to be absolutely enormous? So certainly, I think we need to know the difference between the materials, but I can imagine you guys can do that.
Sure. We can do 10%. If it gets to 3%, it gets harder.
Yeah, yeah, no problem. Yeah.
Down here.
Hello. I'm just wondering how the density of ice varies with pressure. Like when you get down to the Uranus pressures, what is the density of ice?
Oh, certainly there are people who worked, I can't think of it, I can send you the paper. I can't think of it off the top of my head, but there's big changes. So ice 10 is ice 7, sorry. So if you were to take water at room temperature and you compressed it, you would go straight away, because you go to the liquid, ice 6, confusingly, and then ice 7 before ice 10. But the structure of ice 7 is a network of two layers of ice 1H. So it's basically double the density of freezer ice. So it's literally the hexagonal one, and they interweave another one in between. So that's an example. And so ice 7 is the sort of probably the most dominant geophysical ice. It's the ice we expect to be mostly in the planets, aside from ice 10. And so ice 10, you're looking 3 to 4 times the density, probably at the bottom of Uranus. So yeah, very, very dense. So those water molecules really don't want to be next to each other.
About the same density as silicates, I think.
Yeah, that's true, yeah.
We have one over here. So ice that looks like rock when we measure its density for exoplanets.
Yeah.
You spoke briefly about the axis that Uranus spins on and how that is about to change from a long winter for the southern hemisphere. Mm-hmm. Can you tell us a little bit more about that? Is that because of precession, or does it not always point towards the centre of its orbit?
I think no one really actually knows why the rotation axis is completely, it's to say. So on Earth, our tilt is what, about 5 or 6 degrees? I'm going to be called up for a bit that wrong. And it's that tilt that gives us the seasonal variability. On Uranus, the tilt is 89 degrees. So that's why it rotates like this. And so as it moves around the sun, you sort of have one hemisphere pointing dominantly towards the sun at any one time. So at the moment, it's just gone through its equinox. It's actually been very interesting time with Uranus. A lot of people have, I think part of Uranus's problem is that Voyager went past when I think one hemisphere was very much in winter and one was in summer. And so everything was very calm. And so you just see this calm blue dot. Nothing seems to be that interesting. Now we're coming through equinox, and it was something that amateur astronomers started to notice. They're actually seeing giant storms, and for want of a better term, they are giant methane storms on Uranus. And that's because you're getting to the point where the half of, or the hemisphere of Uranus that has been in winter for the past 20 years is starting to warm up. And at the same time, and everything's mixing and turbulent, and that's why you're getting all these storms developing. So it's a very, very interesting time, and I think, and on the basis of all that amateur data, some professional astronomers used the Hubble Space Telescope to look at Uranus and to see these clouds and weather changing. And so we expect for the next, I imagine, 3 or 4 years for Uranus to be a very interesting place before it moves round. And then you get the next hemisphere, so I think it's the northern hemisphere is going into a very long winter, going into a 20-year winter in the southern, and it will go quiet again. So that's kind of how it works, if that makes sense. So that's good.
around for more hands. So I've got another question. I've got heaps of them. So if we go to Ganymede, right? So with all its layers, so Earth has some layers, and we find out about them through seismometers, like you said. Could you, if you put a seismometer on Ganymede, would that help, or would you need to make explosions as well to see the earthquakes?
Yeah, that's a really good point. Well, if Ganymede naturally had Ganymede quakes, then you wouldn't need to make explosions. Now, that would then necessitate for you to then think, is Ganymede geologically active? So we know that the surface of Ganymede is really young. So like Europa, we don't see many craters on the surface. So certainly that would point to the fact that, yes, something's going on. Now, whether the frequency is like on Earth, where we have quite large earthquakes very frequently, or whether it's on the frequency of 10,000 years, we don't know. So you could take the risk and go and put a seismometer on Ganymede, and I know that several of them have been developed to go and bury into ice and to sit there and wait. And certainly as soon as you observed an earthquake, you would be able to tell a lot. It would be better if you had another one on the other side and things like that, but of course, you know, one can never, beggars can't be choosers. But yes, the concept of going there and making a big enough explosion is quite scary, actually. I suppose, yeah, you could land it and then later on actually crash the spacecraft into it. Yeah, you could do that. But there's this big thing called planetary protection.
Oh, yes.
Yeah, they probably wouldn't let you do that. Yes. Oh, there's two. Oh,
Whoever gets there first. I think we are here first. And then here second.
Good evening. Thank you for your talk.
my pleasure.
I'm fascinated. One of the things which has come up in the way you described our satellites, our solar system, is that we get 4 rocky planets, then we get 4 gas giants, and then we get whatever you believe about Pluto. And if you compare that to what we've seen so far of some exoplanet situations, you might get a star with a massive hot Jupiter right near it. And it seems that there seems to be a lot of variation in how solar systems can form. Is an interest of yours the theories of how we end up with this distribution of planets?
Oh, absolutely, for sure. I mean, you shouldn't be, you know, unless it's, I think that's, yeah. Yes, I am interested.
Yes, and to focus
I think
the question,
a lot of our problem is that for a long time we were the only solar system we knew. And then, of course, when we started to observe, and we're observing these very big planets that are very different to us, and they orbit a lot closer to a star, we're like, oh, maybe we're a bit unusual. But of course, that was until, was it earlier this year, where the TRAPPIST-1 solar system was observed. It was just amazing. You wait for an Earth-like exoplanet and 7 come at once. It's just amazing. But they're all terrestrial planets, or at least thought to be at this stage. I mean, it would seem that the way our solar system works is a sort of consequence of chemistry. You go from the heavier stuff falling out the planetary disk first, and then the lighter stuff falling out, and then with because all the gas giants on our solar system occur beyond what we call the ice line, so this point where ice could fall out of the protoplanetary disk. But and we've seen other systems with these ice lines, or at least I know people have observed like a carbon monoxide ice line where you can see carbon monoxide freezing elsewhere. The really nice one, like for instance, is Ceres, which is the asteroid, which sits very close to the ice line, so has some ice on the surface, sort of like mountains on the side. And then, of course, Pluto is whatever's left over, but Pluto potentially didn't come from there. It's probably been shoved out there. And I think that's the thing. Pluto has been the start of the discovery of Pluto, and well, obviously Pluto was discovered a long time ago, but the discovery of being such an interesting world has really, I think, shaken the tree in what we think about of how our solar system has formed. And I think that my view that I just reiterated of the chemistry falling out and it all being very neat is quite an old view now. And things are changing. I've seen talks where people suggested all the gas giants flipped around and they moved around and things like this, and they caused all sorts of waves around. So I think that's a lot more still to go. And then, of course, the more exoplanets we discover, the more we'll know that how unusual. So it could be we're just one end member of one thing. And I think that's the most exciting thing, isn't it? That we're just one type, and there's a bigger variety out there for us to explore.
Thank you.
Up here.
Hi there.
Hello.
Oh, you talked about how we have seismology to thank for a lot of the things we know about what's in the center of the Earth. And you also do experiments in the lab where you compress and, I think, heat up like diamonds. So I'm just curious, what kind of things have you found in the lab which you maybe haven't found in seismology?
Oh, I see. So the seismology, at least on Earth, gives us an idea of at least the density variations. So as you go through Earth, you get, it's good to get two types of waves. You get the P waves and the S waves, and you can see the velocity of them change. You can see them moving faster through the denser material. And that's how we've built up this model of Earth, of the layers that are coming through, and even down to the liquid, where the shear waves can't go through, the S waves just stop. They're like, oh, I can't do that. But the P waves carry on through. So that's been really, really nice. So that has given us a great idea of the density, which of course is a great thing. And then of course, all the diamond anvil self people have just been going and mixing up stuff and trying to match the densities. So essentially it's not a one or the other. They're very much working together towards exploring. You couldn't do one without another. And certainly, as you found, one of the big mysteries in geophysics for many, many years was the fact that just before you get to the liquid part of the Earth, there's this thing that was called the Ddoubledash layer, and it was a layer of extra density that we could never quite understand why it was, until about, I think it was 4 or 5, no, probably much as 6 or 7 years ago, some Japanese and American researchers at the same time discovered that you get this perovskite structure, which I talked about, can densify even more. And straight away, they're like, right, that explains the Ddoubledash layer. So it was a really, really nice example of using that experimental work to explain an observational phenomena. And essentially, that's what I do now, is I take sort of the observational data and I try and explain how that's happening through lab experiments. So, yeah.
Another question down here, and then I think we'll wrap it up after that, unless there's anyone desperate.
You've been put in charge of the next Voyager dispatch. Where are you going to send it?
That's a really easy question for you, and thank you for promoting me so highly. It's not surprising me, but I want to go to Uranus and Neptune. So they're now getting to be the only planets that we've not sent. We've had one, I think, Neptune's had one flyby. Uranus might have had 2, I think, now. Now, the thing for me is not only to study those planets themselves, because they're very weird from these magnetic fields. You know, you just need to look at what Juno has discovered at Jupiter. I mean, when Jupiter has thrown us up so many surprises, imagine what Uranus and Neptune are going to do. I think it's just going to be crazy. But as an added bonus, they also have loads of really interesting icy moons. Neptune in particular has Triton, and it could be a lot of, and Triton's again very weird because it goes round the wrong way. Everywhere else in the solar system goes round one way. Nope, not Triton, I'm going to go the other way. So not only that, and we've also seen active volcanism on the surface of Triton. We think there's big geysers of I think it was Voyager saw these big geysers of nitrogen coming off. So we know there's active geology there on Triton, and we know that those gas giants are just going to be an absolute marvel to study. So that's where I would like to go, please. Thank you for that. That was a great question.
Sounds very exciting. Plenty more discoveries to be made. So let's thank Helen again. So I'm sure that you all found this as fascinating and as enlightening as me. So thanks also. So we're also going to have the video made online with the YouTube channel, so you can see bits that you missed, because there's quite a lot of information there. So this is just one of a number of public events and activities the Academy is aiming to, is putting out with the intention of improving public awareness and understanding of science. So other activities of the Academy include engaging school science programs. There's the thing called Primary Connections, which I hope you've heard of, and Science by Doing. There's a new maths program called Resolve, and there's also a website, which I hope you'll go to, called nova.org.au with plenty of good material. The Academy is also a not-for-profit organisation, and I'd like to thank each of you who supported the Academy, supported us for purchasing your ticket to tonight's event. And so this helps to bring speakers and important topics to a broader audience. So there's other ways to support the Academy, and you can make a donation by visiting the Support Us pages on the Academy's website. So thanks again to the sponsors for this evening. That's Jira Wines, a Geostation, and Edge Catering. And hopefully we'll see most of you back here for our final talk in this series in December. So thanks again.